So today I'm going to talk about time series for scikit-learn people. So what I kind of mean by that is I'm going to talk about time series forecasting using like the language of regular machine learning or kind of conventional machine learning, and talking through some of the code and implementation for basically from the framework of anybody who's familiar with using scikit-learn. And I'll dive into that a little bit more. Just to give you a little bit of background on who's talking to you up here, I actually recently founded a company called Enhance AI, where I focus on building a product to help data scientists to monitor the true performance of their machine learning models once they're in production. And so if any of you are dealing with that or just want to vent to me about productionizing machine learning models, then please come up and talk with me after. I got the idea for this company after spending a year doing data science consulting here in New York, independently, building full stack products for different types of companies. Also ran a machine learning team and worked as a data scientist at two different retail startups here. And then prior to all that, did a PhD in physics at Columbia here in the city. So a lot of what I'm going to talk about today kind of was born from some blog posts that I wrote as I was getting interested in time series modeling. So if you're interested, those are all on my website. And then the typical places you can find me online are either on Twitter or on GitHub. So just to kind of get us all grounded is that we're using the same terminology. Just wanted to give a very brief intro to what is a time series. So kind of at the simplest standpoint, it's basically a number that depends on time. So kind of everything is a time series. I think everything depends on time, but there's kind of standard types of data that we deal with that, let's say, more obviously depend on time. So as an example, Uber has like entire teams of people that work on forecasting time series. And so, for example, something they might want to do is forecast how many trips are going to be taken on a given day. So they have historical data where they know how many trips were taken on a day in a city, and they might want to forecast this. You can imagine as a company that loses billions of dollars a year, they might want to reduce the amount of money that they're losing. And so if you can forecast how many trips will be taken, then you can make sure that you have enough drivers available and things like that. Other big companies deal with these types of problems. So Amazon has a nice paper on the archive and where they talk about predicting how many sales a product will get in a given week. And I've worked in retail before, and so I know that this is a thing that companies have to do because you have to buy your products ahead of time. And so if you overestimate how many sales you expect to get, this can be bad because you don't sell all of these products, and then all of your money is tied up having bought these products that you can't sell. So these are kind of like big multi-million-dollar applications of time series modeling. For me, I was focused on something much simpler and kind of trivial. We have a bike share city here in New York, which is kind of one of, I guess it's like a legacy one. It's not dockless like these new ones. Instead, we have these stations, and there's a finite number of docks where you can dock a bike. And I had this issue at my last job where I would look up online to see how many docks were available at the station near my office, and it would say that there was some docks available. I'd ride my bike there. By the time I got there, there'd be no docks available, and I'd have to, go find the next nearest station. And so it was a minor inconvenience, but I was like, I should have been able to know ahead of time that by the time that I got to this station, there would be no docks available. So a couple years ago, I set up a little system to start tracking this data. So the City Bike has an API where you can request from that API to find out how many bikes are available right now at every station. And if you set up something to continually request, then you can start to track this sort of data. And so this is a time series. These are the number of bikes that were at a station near my old apartment where I lived. And you can see that there's like a daily periodicity to this. And in fact, if you look closely, you can see that I live near a commuter destination. So I was near Union Square, and so there's a lot of offices around there. And so in the morning, everybody would ride a bike to Union Square, and you can see that the number of bikes at the station would rise and basically max out until every dock was full. And then at the end of the day, everybody would take a bike and ride home. So this is kind of how I got interested in this, and we're going to come back to talking about the city bike data. But may before we get into that, I kind of want to tell you a little story of how I ended up learning about time series. And so, like many academics who didn't know what they wanted to do after grad school, I spent my last year wondering and decided, all right, I think I'll do data science. And so I studied a whole bunch. And one of the first classes I took online was this machine learning class by Andrew Ng, which is fantastic, and it's free. And I was going through this class and learning about what is machine learning. And so in a single slide nutshell, with machine learning, we have some target that we're trying to predict. So that's going to be the y in this equation. That's maybe it's the number of bikes that are at a station. Maybe it's whether a customer will purchase a product. You then have some model f where you can put in some data that you know. That's this X matrix. These are the features of your model. This is data that you know. And then the goal is to figure out the best parameters of this model to be able to predict that target. And so that was all fine and good to me as a physicist, because I learned a lot about calculus, and I was like, all right, we can take this function and minimize it and everything else. But the nice thing is that nowadays we don't have to know math anymore. So we have scikit-learn. We don't have to know calculus because we have auto differentiation libraries, and it's great. So with scikit-learn, you can just import a model, let's say a linear regression model. And they've kind of distilled all of supervised learning into this very simple API where you can fit the model on some data. So you pass in your features, the data that you know, and then the values that you're trying to predict. You fit the model to learn the best parameters, and then you can take new data, pass it in, and create new predictions. And so that was kind of really nice when I realized that all of this existed and you don't have to code it by hand. But then I went to go look up time series modeling, and it was like this whole nother world. So there's all these warning signs about make sure your data is stationary and don't piss off Gauss and Markov and everything else. And so it felt like something completely different. And so I got to work and started writing out these weird lag matrices and all of this other crap that you have to do. But then, I kind of got so far away from machine learning, I was wondering, how do I connect these ideas? And so one of the questions I was asking myself was, like, how do I add features to a time series? Like, if I know what the weather was like, how do I use that information maybe to predict a time series better, to maybe predict how many bikes will be available? And so that was kind of confusing to me. The other thing was that as I started working at a job and actually starting to deploy code, it started to terrify me when I thought about how would I actually deploy a time series model. So there's lots of Python libraries for time series modeling, but oftentimes these libraries, the data is kind of intimately coupled with the model, and the data might even be like an attribute of the model. And so when I thought of how do I deploy this where I take in this brand new data, it gave me nightmares. And so that's where I kind of like set out on this task to try to connect time series to kind of conventional machine learning. And so the first question I wanted to answer was, if I want to try to think of time series like I think of scikit-learn stuff, was like, where's the X matrix? And the problem is that with the time series, there is no X matrix. There is only the Y. There's only, at least from a simple standpoint, there's only the value that we're trying to predict. And so it felt kind of confusing on what you're supposed to do here. But it turns out that you can, in fact, build out an X matrix. And so one of the simplest versions of time series modeling is people create these things called either autoregressive or lag features. And the idea, which sounds like you shouldn't be allowed to do this, is that you use the thing that you're trying to predict to actually create features to then predict it. But you make sure that what you're doing is that you're never leaking the future into the past. And so what a lag feature is you define a window. In this case, we want to predict these Y values. And I've created a window size of 5. And so what we're going to do is we're going to say, let's use the previous 5 values of the time series as features in order to predict the next value. And so for, let's say, the 5 right here, we're going to use the previous 5 values of the time series. These will form the features of my data, and we'll try to use these in order to predict this. If you have a single lag feature, then this is, and I guess if you have no model, then this ends up being like a random walk. But the idea here is that, yeah, you define a window, and you just use these previous values in order to predict. And in Python, it's not so bad to do this. You write a for loop, and you kind of apply this moving window. And so more visually, what this ends up being is that we can take our time series and we can chunk it up. So every red point here is a value that we're trying to predict. And so each of these red points, this is kind of the same time series stacked on top of itself. Each of these red points, we can extend them all along and form them into the target array that we want to predict. And then we're always going to use the previous values as our features. And we can kind of stack all of these blue lines on top of each other, and that will give us our X matrix. And so just to be concrete about this, typically when you think of this X matrix or this feature matrix or this design matrix, each row is a sample or an observation that you've had, and each column is a different feature that you're going to use. And so then each row of X corresponds to each element of Y. So one of the nice things is that once you have an X matrix and you've created your Y array, now you have the entire world of scikit-learn at your disposal. So if you want, you can import a linear regression model and you can fit that. And in fact, that is an ARIMA model just with the auto-regressive terms. One call out point that I'd like to add here is that everything I'm going to talk about in the framework of scikit-learn, it works for some parts of time series modeling, so it can work for the autoregressive terms and the integrated terms, but you actually can't create moving average terms if you're familiar with that, because that ends up being a nonlinear PDE that you can't solve with scikit-learn. But if you're willing to throw out a little bit of functionality, then you gain a lot of the functionality of scikit-learn. And so, yeah, you can throw a linear regression model on, but you can also throw a random forest on if you want. Why not? You can throw XGBoost in there. You can find the latest fancy temporal convolutional neural network if you want, and you can try to fit your data with that now that you have created this X matrix. And now that we've also created the X matrix, we can go back to answer my original question of how do we add features to this time series. All you have to do is you can just stack your features next to those other features that you've already built. So if you imagine that you have other features like what is the weather like, or what is the state that the time series is in, or something like that, or the city, you can just stack that information next to it, kind of horizontally concatenating it. I've made this look really easy here. Probably the hardest thing in lots of data science is dealing with time. And so if you can get your data to be lined up perfectly with time right here, then it's easy to stack these features in. But oftentimes, one of the hardest parts is reconstructing the state of your system at the point in time that this time series related to. So I'll leave that as an exercise to the reader. So now that we have, done this work to get our X matrix, now we can think through how we would want to deploy this. And so I was really excited when I figured out how to create the X matrix and that I could just throw random forests on everything. But there's kind of a couple things that I've glossed over here around how would we actually deploy this. So one of these is that I talked about how you can build out these lag features using the previous values of the time series to predict the next value. But if you think about the earliest values in the time series, they don't have any previous values, or they maybe don't have enough previous values. And so that doesn't really work well with scikit-learn, where you expect that, let's say, your X matrix should have the same number of rows as the length of your Y array. And so you're going to have to figure out how you're going to handle this. The other thing is that oftentimes people do pre-processing on their time series. So a very popular one is you difference your time series. And so what that means is you take each point in the time series and you subtract the previous point from it. And so this is a way to kind of like remove a slope from your data or remove a trend. It's actually kind of like a numerical derivative. And so, but what people often do is they first difference the data, and then they fit a model to the difference data, and then they need to undifference the data afterwards. And so thinking through how you end up doing this, there's a little bit of functionality recently that's scikit-learn has this. When I first started this, they didn't have this functionality. And so for that and a couple other reasons, I ended up building this library called skits, which is like scikit-learn inspired time series models. And the goal is to make everything as compatible as possible with scikit-learn. And so if you want to check it out, it's on my GitHub. It's pip installable. And so you all should be able to play along. And I have a bunch of blog posts where I talk about using it. And to be clear, there's lots of other Python libraries for time series modeling, some of which are compatible with scikit-learn. A lot of what I did here was kind of as an exercise in me learning this stuff. But I hope that it's useful as well, and I will follow up this, or towards the end of this talk, I'll talk about productionizing this. And so one of the things that I set out to solve was this issue with these lag features where you're missing them for some stuff. And so skits has an autoregressive transformer, which is subclassed from scikit-learn's transformers. And what it allows you to do is define the number of lag features that you'd like to use, and you can transform your data with it. So one thing to note here is that kind of with anything in skits, you just want to make a copy of your data. So let's say I'm predicting this y. I just make a copy of it and make sure that it has a column in it before transforming it. And what's going to happen is that when you pass it through this transformer, we make this stupid assumption that everything is null in order to preserve the shape. And then you can later impute these nulls if you would like, and use one of the imputers in scikit-learn. As well, with differencing, there is a differencing transformer. And so you can pass your data through the difference transformer, and it will calculate the difference between adjacent values of the time series. So, for example, the difference between 5 and 2 is 3. And it'll also make sure that that first value is a NaN because there is no previous value. But then there's also this reversible imputer in there because I wanted to make sure that I could get back to where I started with everything. And so first we can impute this NaN value to at least fill it in with some number, because you typically need to pass numbers into scikit-learn models. But then the other key thing here is that if I want to inverse transform like both of these transformers, then I get back to exactly where I started. And so what this allows me to do is be able to generate predictions, like generate time series forecasts on the exact same scale as the data was originally in, even if my models are operating on some pre-processed version of the data. Okay, so we've been talking about transforming data and things like that. The next step is, how do we actually generate forecasts? How do we try to predict the future? This guy is a chief futurist, in case you didn't know. So the standard way that people do time series forecasting is they use this thing called recursive forecasting. And so what you do is you have your data, you feed it into your model, and you predict the next value in the time series. And you actually optimize your model to be able to predict that next value. So that's really the optimization that's occurring. And then the way to predict multiple values in the future, maybe I want to forecast the next week, is I pass that prediction back into my model, and then I go on and predict the next value, and I keep kind of passing it back in. And coming from like the machine learning side of things, this is kind of crazy to me because we're directly optimizing for that next step, and then we just hope that when we recursively pass stuff through, everything will be okay. And it seemed to me like we should be directly optimizing for what we want, and if we want to predict the next 10 values, then why don't we directly optimize for that? And so this is called horizon forecasting. And so you can actually pass in the next 3 values of the time series as your target, and you can directly optimize to be able to predict all of them. So it's kind of a multi-output regression is what this ends up being called. And so visually, what this ends up being, if you remember before, we could kind of move along and have this sliding window in order to predict those next values. Instead, we can just predict the next 5 if we want to. And one thing I want to call out here is that I've been a bit glib in how I've described recursive forecasting. Typically, people use like well-founded statistical models when they build these things, and if you care about like the uncertainty in your time series and injecting domain expertise and causation and correlation, then oftentimes like this stuff is somewhat guaranteed in recursive forecasting because you've designed these statistical models to actually encapsulate how the behavior should move along as you feed data back in. On the other hand, if you're willing to give some of that stuff up and you're okay with things being a bit more of a black box, such as I just want to predict the number of bikes somewhere, then you can take this more machine learning driven approach. And so skits has a horizon transformer, which you can pass in the target array, which you're trying to predict, and it will go through that target and generate the next however many targets you would like to be able to predict. And so that's where you define the horizon here. And if you look, it actually kind of looks like the autoregressive transformer. But the idea here is that you end up wanting to transform your target such that you're predicting multiple values in the future as opposed to a single value. So I don't want to go too deep into this, but kind of the last step of all of this and what I wanted to do to be able to deploy these things was to group everything into a pipeline. And so if you're not familiar with scikit-learn pipelines, it allows you to chain transformers together, lots of transformers, and then kind of throw an estimator or a model on at the end in order to encapsulate all of your logic into one giant object. And so skits has a forecaster pipeline, which is based off of the scikit-learn pipeline. One of the things the forecaster pipeline does is it allows you to operate on the target. So typically everything in scikit-learn, all of your transformations take place on the X matrix, the design matrix. And you kind of have to leave the Y array or the target alone. The forecaster pipeline knows what's going on inside. So it knows that when we want to transform our horizon, we only care about the target that we're transforming, not the original data. We can make sure that certain transformers only operate on the target. You can construct a whole bunch of features, and then you can throw your model on the end. And it typically behaves like a typical scikit-learn pipeline. You can do recursive forecasting with it, so it has that capability, but you can also just directly predict your horizon. Yeah, and so kind of the other thing to point out, I didn't really know this about scikit-learn before I started doing this, but let's see, linear regression, you can have a multi-output that you predict, so like a multi-output target. And then scikit-learn also has this nice thing called a multi-output regressor, which allows you to train an individual model for every target that you're trying to predict. So if I'm trying to predict the next 10 values in the time series, and you have a lot of compute and memory and time, then you can wrap any model you want in the multi-output regressor, and it'll train an individual model for every output. Throw XGBoost in there and all sorts of other things. So I have a whole blog post where I talk about this, but I ended up kind of running this analysis on some of the city bike data that I was collecting, and I tried out a linear regression model, an XGBoost model, and then a fancy deep learning model. And like with most things, XGBoost performed the best. Linear regression was a lot faster, and so that's what I ended up designing and deploying. So let's get to the deployment stage. I mentioned how I collect this time series. I collected this time series of city bike data. It's been collecting since like 2016. I think I have like 500 million rows of data or something like that. But the way this thing works is I have a little Lambda function on Amazon that pings the city bike API every 2 minutes. It grabs, how many bikes are at every station in the city right now, and it writes that data to S3. There's then another Flask app that I have where I have a little Lambda function every 15 minutes that pings the Flask app and says, hey, start making some forecasts. And so the Flask app has 1,000 models that I've trained for the 1,000 stations that are in the city, running on this tiny little EC2 instance. And then PyData shout out, I have a little local DAS cluster that's running, which allows the Flask app to submit 1,000 forecasts to the DAS cluster. And each of these tasks, we generate a 2-hour forecast. So in 5-minute increments over the next 2 hours, how many bikes will be at every station in the city? And I actually built this whole thing to stress test the startup that I'm designing. And so every time I generate these forecasts, I send the forecast information to my system. I also send some historical data showing how many bikes have been at these stations over the previous 2 hours. And so all of this, it ended up being pretty easy to deploy this whole thing. And I guess real quickly, I will show you a quick demo, which maybe you all can see. So this is the city bike station near my current apartment. And so I was able to track how is my model actually comparing to the forecasted model. And typically when you're doing machine learning work, you kind of, you create this test set and you calculate some error metrics on it and you get a single number and you try to get that number smaller. And so I had done this originally when I was training these models to try to see how they're performing. Once I kind of got it into this view where I could look at my forecasts over time. So this is a 1 hour ahead forecast. So when I predicted an hour from now how many bikes will be there and how many bikes were actually there, I was disappointed to see that, in fact, your error is not just a single number over time, and your error changes with time. And so the model ends up being pretty good at predicting when nothing's going to change, but probably when you want to predict that things are going to change, I mean, the model's okay, but that's where you tend to kind of see how the error changes. And I guess real quick shout out, PyData shout out is that all of this I built using Panel because I only know how to program in Python and MATLAB, and nobody's going to build a dashboard in MATLAB. But Panel is a great, very new library for building interactive dashboards in Python. So just to wrap up, I have this library called Skits. It's on my GitHub. I wrote a lot of blog posts about all of this, which should be easier to get through than this fast talk. And thank you all for your time. And I'm happy to take any questions.
Your forecasting pipeline, is it by chance compatible with TS Fresh's feature augmenter? Can you drop that in your forecasting pipeline?
I don't know. So I had played with TS Fresh a little bit when I was looking into these things, but I don't recall exactly how the API works for it. And so that would be something interesting to check out. So the question was around how to featureize the shape or trending behavior. So I think there's different ways. There is a trend transformer within skits, which I'm trying to remember exactly what it does. But I think in that scenario, you just learn an individual feature, I think, for every element of the time series. No, actually, I don't quite remember. So in terms of shape and trend behavior, I think there's different ways to do it. Fourier features is kind of a nice way to handle this in a more black box manner, where you can build out different features that are related to different frequencies that might exist within the data. So.
Have there been like open source contributions to Skit, or is it basically just you at this point?
There's been one. It's very welcome, very surprised. It's largely just been me so far. I worked on this a lot last year, and then I've been busy with this startup and things like that. But open source contributions are very welcome. I recently ran black over all the code, so at least it's formatted nicely. But yeah, everybody's welcome. Please contribute. So
when you do the differencing to remove the integrating factor, so it becomes stationary. That's the goal of it. Should you check that the differencing is enough? You run VLP test or something to check.
yeah, so the question was around differencing the data and making sure that the differencing was enough to actually make the data stationary.
2 times or 3 times.
Yeah, so sometimes people will difference the data 1 time or 2 times, and there's actually this entire recipe around how you should be doing this. So I kind of glossed over stationarity here, and kind of the reason I glossed over it is that it took me a while to figure out, like, why do things need to be stationary? So there's lots of textbooks that will talk about this and blog posts that talk about it. And as far as I could understand, if you want to be able to basically use statistical guarantees to quantify the uncertainty in your model or quantify correlation, then you need the data to be stationary given the type of model that you're using for generating the forecast. But you can also not care about that. So it's fine if your data isn't stationary in the sense that if you just want your model to be able to predict, and as far as you can tell the model predicts based off of all of your offline and online experiments, then that's okay as well. And so I think, Yeah, so there's kind of, yeah, there's the recipes to make sure that it's stationary, and you can do that, but I guess it's also, it just depends on what the application is.
Yeah, so you said that you use this CityBike project to sort of stress test this method for your startup. So have you modified it since then, or does it look exactly like this?
Still looks exactly like this. I've mainly been focused on building out the startup side of things, and I just needed a forecast to be generated. One thing I'd like to do is track different types of models. So in my offline experiments, I found that XGBoost performed better than a linear regression model, and so it'd be interesting to be generating multiple forecasts to see how these behave.
Have you ever used the prediction yourself of the model for your community?
Not yet. I recently got this up and running. I would like to create an API where I can just ping my model to see what is the forecast exactly right now. I've also been working from home, and so I don't really have the original issue that I had of commuting. So, blessing and a curse.
What sort of derived features did you create for the data?
So with this, it was literally just autoregressive features. That was it. I think, so with the model that I ended up building, I just took a week. So I think it's sampled in 5-minute increments or intervals. And I took a whole week of data as the feature. And I'd originally, there's like seasonal transformers and a bunch of other things in skits. And I originally tried all of that. And it turned out that just shoving a week of the previous values through did decently enough.
Did you try and bake in days as a feature as well?
Yeah, so I think dates would be particularly interesting. Like Sundays are very different than Monday. Like Monday morning is a very different day for city bike data because people did not commute the day before. Weather is probably a huge one, and then like holidays, the marathon yesterday, things like that.
Are you upgrading all 1,000 models every 15 minutes?
Definitely not. Yeah, so I originally trained them all. I trained all 1,000 models on AWS Batch. And then they all sit locally on the instance that I'm running. And I'm just using those models, and I haven't retrained them because I actually kind of want to observe how the models decay over time. So
you mentioned that you have some invertible operators. Can you put them in the pipeline after the estimator?
yeah, so yeah, you can. And that was, well, yeah. So you can do that with, actually, let me think. I don't know if I can put them, I think you can put them actually in the pipeline. Yes, you can. And so that way, everything that you're predicting is on the exact same scale. Because that's what worried me. Even if you pre-process your time series ahead of time, like if you normalize it, right, then what you end up predicting is on the normalized scale as opposed to the actual scale of the data where like the end user would be using this forecast. So, yeah.
What are sort of some of the like feature sets and the time series methods that you think would sort of benefit most from having sort of like scikit-learn type interface with it?
I guess methods or applications?
I guess either. Okay.
Yeah, I think basically low risk time series is probably the area where you want this. So if you're like large-scale economic models that are going to influence policy, you might want to make sure that these are more statistically grounded than these more machine learning-y black box approaches. But I think oftentimes at lots of companies, they just need something that's better than an average. I've worked at lots of these companies where you have people who have built out averages, and maybe they just use the previous average as their future prediction, and they just want something that's better than that. And so if you want to be able to quickly deploy these things, and just get people something, then I think oftentimes being able to do it in this manner ends up being helpful. I will let you all go because I think it's coffee break, but thank you all.